We have pork shoulder, but we also have bacon. Hey, Raphael, how's it going? Thank you. Thanks. I appreciate that. Oh, all right. It's 5:30, so let's go ahead and get started today. All right. Good evening, everyone. How's everyone doing today? Good. Thumbs up. Thumbs up. Yeah. Thank you, everybody. Oh, go ahead.
Great.
Good. Good. Yeah. Thank you, everybody, for being flexible today. I know it was kind of a last-minute change, but it's with all the variants and stuff, I think you can never be too careful. So I feel like I'm blessed with the technology that I could do something like this, and we can still have class without putting anyone in danger. So I know it's not ideal, but I'm glad that we were able to get our ANSYS activity done last week, and so we don't have to do it this week. And so this week is just a lecture week, and so we can have all the lectures virtual, and it'll be not ideal, but still not too bad. All right, and so the plan for today is we're going to do I think is our last week on meshing, and so we've been talking about meshing quite a bit for the last few weeks, and this will be the last one. And so the title of these lecture notes is called Advanced Meshing, and this is kind of like all of the, I would say, kind of the more advanced topics in meshing, a little bit of a cornucopia. Not everything here is kind of builds off each other, but I think these are all of the I would say really important information that you need to know about meshing that may or may not have been covered in previous ones. And a lot of this is going to be very ANSYS specific too. And so, I've gotten a lot of questions over the last few weeks of, what does this setting do, or what is this, what does it mean when ANSYS gives this setting? Hopefully, this week will answer a lot of those questions. Okay. But before we start today, I did want to do a very quick demo in ANSYS. And so, because I know a lot of you are getting started with the project, and specifically for those of you who are working on the globe valve, I mentioned a feature in there called hide faces. And so I did want to give a quick demo of that, before we begin today, just to show you what it is, how it's used, and why you would want to use it for this particular project. Okay. All right. And so are there any questions I can answer before we get started today? Okay. All right. So let me go ahead and swap to my laptop screen really quickly. Okay, and so here I have the globe valve, and so I know for sure that some of you have already chosen this for your midterm project, and so and I know some of you have already have already run some simulations, which is great. Okay, but if you are working on this valve, then I think a lot of you have already correctly identified that this particular device right here is used for a lot of high pressure fluid situations. Okay, and so inside this empty cavity right here, you would typically have a pretty high pressure fluid that's running through. So be it water or oil or whatever fluid that needs to be transported. Okay. And so one of the primary forces that you're going to be concerned with in this geometry are going to be the hydrostatic fluid forces that come from the fluid, right? Because the fluid is going to be highly pressurized. That pressure is going to exert a normal force on the inside surface of the pipe. Okay. And one of the questions I think is fair to answer is, what's the maximum amount of pressure that this pipe can withstand before it really just starts to burst. Okay. All right, but in order to do that, let's say that you want to apply a pressure force. Okay, so let me just go ahead and right click this, insert a pressure. Okay, and so this pressure force right here that I'm going to insert is going to represent the fluid pressure that's going through. Okay. This force or this pressure needs to be applied at every single interior surface here, right? Because the fluid is going to touch every single surface on the inside, right? And so to make it fair or to make it accurate, you need to highlight every single one, okay? But as you can start to see, because this globe is kind of like this globe valve here has kind of an awkward shape, getting every single interior surface right here is not easy, right? And so you can kind of rotate this, and I've been doing this for a while, so I can kind of rotate, well, but it's not the best, right? And so you can do your best to try to look in through the ports and to see, and to try to highlight as much as you can, but this is far from ideal, because you can try to click everything that you can here, right? But undoubtedly, because there's so many tiny surfaces in here, it's going to be really easy to miss them, right? And if you miss a surface in here where you don't apply pressure on a surface, you're going to get some really strange results, because the assumption that you have when working with a fluid like this is that pressure applies everywhere. Okay. All right, and so instead of trying to look through the inlet and outlet of the valve to try to highlight all the surfaces, an easier way to do it is to simply just hide the exterior surface here. Okay. Because if you look at this pipe, it's a little bit hard to tell from this angle, but there's actually like an inner diameter and an outer diameter, right? And so we have this surface right here. This is the outer diameter, and so you can see when I highlight this, it doesn't highlight anything on the inside, because those are two distinct surfaces, right? And so what we can do, because we're not applying any boundary conditions on the outer surface, is that we can actually just hide these, right? And so if we highlight, let me just kind of group highlight a bunch of these. Okay. And so let's say that we want to look on the interior of this model here, from these surfaces here. Okay. And so we basically want to remove these so that we can adequately click the ones on the inside. Okay. Let's click a few more. All right, that's good for now, right? All right, and so we basically want to hide these from view so that we can have access to the guts on the inside, right? So what you can do is, once you've highlighted all the surfaces on the exterior, you can just simply right-click on your mouse, and then you can click on where is it? This one right here. So this button here called Hide Faces. Okay. Alternatively, you can use the keyboard shortcut, which is F8. Okay. And so when you click on this, right? If you kind of blinked, it kind of might seem like nothing happened, but what happened was that we hid all of those external faces, and so now all we're left with is just the interior ones. And so when I click on this outer surface right here, then this is going to highlight the one on the inside, which is what we want. Okay. And so now to select all the interior surfaces, so let's say that we want to apply a pressure on all of these. Okay. It's really easy now, because the outer surface is out of the way. We can just go ahead and click every single one in here, just like that. Okay. All right, and so that's a question.
Yeah, I have a question. Is there a way that we can change the settings so that it highlights better? Because like when you were highlighting, I'm seeing that it's like only highlighting those white outlines, like at least from the outside point of view. And I could see that it would be easy to make a mistake and unclick one. Is there a way that we can change the setting to get it to highlight green on the outside?
Yeah, that's a good question. I've actually never tried. I agree. I think that would be a really useful setting too, because even though you can kind of see it from here, and you can kind of see the green outline, it would be very easy to kind of say like, oh, did I click that one yet? And then you click it again, and then you deselect it. Yeah, I'd have to see. It might be somewhere here under the display settings. But I think because by default that the outer shell should be there, and so the reason when you click this and it only highlights green on the inside is because this is not something that ANSYS typically renders, because there's something usually on the outside blocking this. But I'd have to look into it, and so I can look into it and see for Wednesday, because on Wednesday I did want to show you something different too. And so I think another application that and I kind of just forgot to do this today, is I wanted to show you guys how to apply a point force as well. And so I need to look into that. And so for Wednesday, let me look into seeing if I can change these display settings, and then we'll talk about how to apply a point force on Wednesday too. Yep. No love for the pairing housing.
Okay.
Oh, go ahead.
No, I was just saying thank you.
Oh yeah, the bearing housing, it's yeah, and so Kamal actually came up with something good for the bearing housing too, which I didn't prepare for that, and I apologize for that too. And so Wednesday, I think we'll also cover how to do a symmetry cut, which I think will be of interest to you bearing housing people as well. But I did want to make sure that I covered this one, because hide faces is something that we haven't covered in an activity yet. And I think for this particular project, I think it's really important if you want to get all the inside surfaces. Yeah. Mm-hmm. All right, question. So is there a way to get a section view to select the interior? Yes, that would also be very very useful as well. Let's see. I believe it would be probably somewhere under selection right here, or maybe under environment. That would have to be another thing I'd have to look up. Just to make sure that I would get it done. I give you guys the right instructions. So yeah, so we'll cover those. How many is that now? Those three. We'll do those three things on Wednesday. So Wednesday we'll cover how to do point forces. We'll learn how to do symmetry cuts, and I think by learning how to do symmetry cuts, it will also teach us how to do sections as well. Yeah, so we'll do those three things on Wednesday, and so I'll yeah, I kind of got caught up doing other stuff today, so I kind of forgot about it. Yeah. Okay. Yeah. Well, let's do those three things on Wednesday, just so that we're all kind of familiar with stuff, because that all those are really useful features. I just don't have experience doing them in ANSYS just yet. Yeah. Okay. All right. Any other questions on this before we move on to the lecture notes? Okay. All right. So let me go ahead and move back to iPad. All right, and so let's go ahead and start the lecture for today. Okay. All right, and so the topic for today is advanced meshing. Okay. Oh, one more announcement. And so I don't know if I'm going to be there on Wednesday, but I did instruct the department to open the door for you all for the computer lab. And so if you want to work in the computer lab, if you want to view the lectures from there, or if you want to work in there afterwards, like you usually do, the door should be open. I did.
I'm in there right now. It's open. I'm in here.
Okay, great, excellent. Yeah, and so I've instructed them to do that all week. And so the lab should be available for you guys, for the whole week. Okay. All right. So advanced meshing, and so we've been talking about meshing a lot, over the last few weeks, and because it's really important. And this, I think, will be kind of the last week where we kind of focus just solely on meshing. Okay. And so we've done a lot, and so we've kind of gone over kind of the basics of meshing, kind of what that basically means, and the basic settings. We've gone over all the element types, and so all the common ones, and we've gone over shell and beam elements. Okay, but in reality, even after this week, there's still so much meshing theory out there, and honestly, a lot of it's kind of goes over my head too. I had one colleague of mine that really was an expert at meshing stuff. And, you know, I remember in grad school, whenever I would have issues, I would always go to him. And he would fix it for me. He would try to explain what's going on, but you know, a lot of times it was hard because you know the algorithms that actually drive meshing software are pretty intense. But with that said, you know, there is still a lot more that we can learn just from an application point of view, from a practicality point of view, that I think will be really useful for, you know, any kind of, you know, practical application of FEM. And so that's kind of that was kind of my goal with these set of lecture notes is, you know, all the things that, you know, we either haven't covered yet in terms of meshing that, you know, that are very common features in ANSYS. I want to make sure I cover those. And some topics that we kind of just breezed over a little bit before, I want to make sure that I give it kind of its proper, you know, its proper, you know, explanation here. Okay. All right, and so the first thing we're going to start with is a concept that we actually introduced before in meshing basics, but it kind of you know drives a lot of kind of what we're going to talk about this week. And so I do want to revisit it. And so that's the idea of mesh quality. And so if you recall from meshing basics, you know, mesh quality is this idea that, you know, some meshes are better than the other ones, and you know, and that's mostly due to, you know, the shapes of the elements. Okay. Okay. Not in terms of, you know, the shape that you select, but after you actually generate the mesh, you know, what do the elements actually look like, right? Right, because remember, you know, when you hit that generate mesh button in ANSYS, right, what you start out with is kind of a CAD representation of your geometry, right? And so you can think of your CAD representation as kind of like space that needs to be filled, right? And so when you hit that mesh button, what ANSYS is going to do is it's basically trying to do basically 3D Tetris, where, you know, you have these kind of set shapes, whether they be tetrahedrons or hexahedrons, and it's going to try to fill that space as efficiently as possible. Okay. And so the unfortunate reality of this is that, you know, ideally you'd want all the shapes to look as beautiful and equilateral as possible, but in reality that just doesn't happen, right? And so because of maybe awkward angles or awkward spaces within your geometry, it's going to have to distort some elements in order to get it to fit. Right. But ideally, you know, when you do mesh a geometry, all of your elements should be roughly equilateral in shape. Okay. Okay. And so remember, what equilateral means is that all of the edge lengths, all of the interior angles, all of the face sizes for 3D elements, all of them are roughly the same. Okay. And so an element that's roughly equilateral like this, we typically call those high quality elements. Okay. But you know, unfortunately, you know, just by the nature of the meshing process, you're going to end up with some distorted elements as well. Okay. And so visually, you know, let me go ahead and draw a couple elements here. Okay. And so I'm going to draw 2D elements just because they're easier to do on an iPad. Right. And so ideally, you know, your element should look like the one on the left right here, right? And so you have all sides are equal, all perfectly balanced, right? As all things should be. But inevitably, you're going to get some elements that kind of look like this. And this one is actually not even that bad. So actually, if you have an element like this is actually okay. But my iPad's only so big that I can only stretch it so much. But you might have elements that are much more distorted than this. Okay? And if you remember, the metric that we use to assess, how equilateral our elements is a metric called skewness. Okay. And so for a roughly equilateral element like this, our skewness metric is going to be about 0, which is kind of where you want to be. Okay. And so for highly distorted elements, your skewness is going to approach kind of the maximum, which is 1. Okay. All right. And so remember we talked about last time, and forgive me too, for the last couple of activities, I meant to kind of put into the activities to check the skewness of your meshes. I know some of you have, and that's great, but we haven't actually done that as part of an activity. Unfortunately, our next activity doesn't lend itself well to it. But for all the later activities and for the final project, this is going to be part of it as well. Okay. And so after you produce your mesh, remember that you can check, what the skewness of your mesh looks like, right? And so remember the way that this does that is ANSYS checks every single element of your mesh and assigns it a skewness score, right? And then what you can do from there is you can check, what's the minimum skewness, what's the max skewness, and what's the mean skewness. Okay. And these are metrics that, go across all the elements in your mesh. Okay. And so, the lower you can get these numbers, the better quality your mesh is going to be. Okay. And so if you get a max skewness of less than 0.6, which is really hard, but if you can, that's great. Okay. And if your average skewness is less than 0.25, which again is really, really hard, but if you can, that's wonderful. Then I would say that you undoubtedly have a very, very high quality mesh. But for most cases, these targets are going to be really hard to hit. So don't beat yourself up trying to reach these targets. They're more ideals more than practical targets. Yeah. Okay. Any questions on this?
Yeah, so Professor, the quality of your mesh, like in terms of these skewness metrics, is it going to be mostly dependent on the geometry of your model, or is a big factor going to be like, okay, can I get this thing to do Hexadominant, or am I going to have to use the triangles, or does that also have play into it as well?
Yeah, it's both. And so there's definitely some geometries that are going to be a lot more challenging to get high quality elements in. That's no doubt. But then there's a lot that you can do with settings in order to try to make it as high quality as you can in those challenging situations. And so there are going to be some cases where no matter what you do, you're going to get poor quality elements. But for all the in-between cases, there's a lot that you can do with the settings, and that's kind of what we're going to talk about a lot of this week. Yeah. All right, and so when we first introduced this, I think we kind of stopped this discussion here, but I did want to talk about why skewness is such an important metric and what effects it can actually have on the solution. Okay. All right, any questions on this? All right. Okay, and so why do we care about skewness a lot? And so I think up to this point you might think that it's just an aesthetic thing, right? And so it does look a lot nicer when your elements are nice and symmetrical and equilateral, but it has a practical importance as well. Okay, and it comes back to kind of the same issue that we talked about with shell and beam elements, which are computation of derivative-based quantities. Nice, yeah. So if you're already using mesh quality, then that's excellent, because that's definitely something to check. it all kind of comes back to this, right? It all kind of comes back to, you know, how well are we computing derivatives in this finite elements? And I know it sounds like a broken record just because, you know, we've literally just been talking about meshes for the last 3 weeks, but it's really important because a lot of times when you're doing finite elements, the most interesting quantities that you're looking for, things like the stress, things like the strain, a lot of these depend on the derivatives, right? And a lot of times these are things that are really hard to measure in practice too, right? And they're the main reason that you're running finite elements, because if you're building a structure and say that, you know, you're doing an experiment, you know, it's really hard to like stick a probe inside your concrete structure to say, you know, what's the stress at this location, right? That's really something you can only do with FEM. And so, you know, I mentioned it a lot because it's you know, it's kind of the golden child of FEM. Right. And so some examples of these derivative-based quantities are things like stresses, strains. So those are the main two structural ones, but, you know, if you're talking fluids, you may be talking about like shear stresses. For thermal, it might be, what's it face? Heat flux. Right. And so the quality of your mesh is going to have a big impact on these, you know, on the computation of these quantities, right? Because remember, you know, the main way that that finite elements compute these is from a finite element solution is through a method called finite differences. Okay. Okay. And remember, the idea with finite differences is that, you know, let me draw kind of an element here. Okay. Okay. And so, you know, in order to compute derivatives, so let's say that we want to compute the derivative with respect to x, right? And we want to compute a value for this entire element. Okay. Okay. And so this derivative will actually have 3 components, because remember, the way finite differences works is that it takes the difference in solution values between 2 nodes and divides by the distance. And so we kind of have 3 different combinations of nodes here, right? And so we're going to have one combination from nodes 1 and 2. Okay, so let's say that we have du dx. This is for nodes 1 and 2. Okay, and this is going to be u1 minus u2 divided by the x distance between them. Okay, so we'll call that d12x. Okay. Okay. Next, we have the contribution from nodes 2 and 3. Okay, this is going to be u2 minus u3. And so this is going to be d23 comma x. Okay, and then we have the contribution from nodes 1 and 3. And so this is going to be u1 minus u3 divided by d13 comma x. Okay, and so we have 3 different ways that we can compute this derivative here. And normally the way that finite elements does that is it kind of takes all 3 contributions here, it kind of averages between them. Okay, and so when you have an equilateral triangle like this, you know, all of these contributions here kind of are balanced, I would say, right? Because all nodes are kind of roughly spaced apart, and so you get kind of a nice computation of this derivative. Okay, because all 3 contributions are roughly balanced. Okay. But when you have a very skewed element where one node is, often, fucking Timbuktu, then, it becomes a lot, this computation can be a lot more unreliable because you have you're computing two nodes that might be in the same vicinity, but then the third node might be in a very different location, right? And so the derivative that you compute from that could be very unreliable. Okay. All right. I should revise this. And so, even though I say here that finite differences are used, it's technically not what ANSYS is using, but I think it's kind of a good way to kind of visualize what's going on, right? And so in reality, what ANSYS is using is it's using the shape functions in order to compute these derivatives. I think we might have discussed that before, but I think this idea of finite differences, I think, it's very illustrative of kind of why skewness is an issue. Okay, any questions on this? Okay, and so let me draw very quickly, the situation when you have a very skewed element, right? So you have a very skewed element, right? So you might have something that looks like this. Okay. Okay. And so if you want to compute derivatives for this, this third node over here, this node 3, is so far from 1 and 2, you might get, very different solution values at this node, right? And so because of that, if you try to compute a kind of an aggregate derivative from all 3 of these nodes, you're not really going to get a reliable answer from this, right? And also just the fact that it covers such a wide amount of space. And so, you have these nodes that are so far apart, when you're trying to compute derivatives on these things, they just tend to be a lot more unreliable unless the solution is not really doing anything interesting in this region. But that's kind of rare. Okay. And so you want to make sure that all 3 of your nodes on the element are kind of equally spaced together, or in other words, you have kind of an equilateral element type. Okay. All right. And so that's kind of the reason why skewness is a factor, because you want to make sure that all 3 of the nodes are roughly spaced the same. And so when you compute derivatives there, those computations are reliable. Okay. All right, and so that's skewness. Okay, and so that's one thing that can affect your gradient computations. Okay. Okay. And so another factor that can affect the way that your mesh is computing gradients is actually something to do with the solution itself. Okay, and so in addition to skewness, another factor that can affect your gradients are whether or not your solution actually has a high amount of gradients. Okay. And so if your solution exhibits a high degree of change in a short degree of space, this is something that you have to be careful of as well. Okay. Okay. And so the key here is kind of those two underlying terms in tandem, right? And so it's okay normally for your solution to have a high degree of change. And so, you know, if you just look at the displacement solutions for a lot of your simulations, then you know, a lot of times that you're going to have zero displacement at your fixed supports, and then you might have, you know, a huge amount of displacements far away. But if that change takes place over a long, you know, over a long space, then that's okay. But the issue that can arise is that if you have a high amount of change in a short amount of space, then you need to be careful about how you mesh those areas. Okay. And so kind of the name that we give for these, for, you know, when you have a high degree of change in a small amount of space, is high solution gradients. Right. And so when your solution has a high amount of gradients, then you need to make sure that you mesh those areas very carefully. Yeah. In summary, you know, you basically need to make sure that you have enough density in there to properly capture all of those change. Okay. All right. And so as an example, you know, let's do kind of a simple 1D example here. All right. So let's say that we're doing a 1D FEM. Okay. And so let's say that we're doing a heat transfer simulation. Okay. And so let's say that we're computing the temperatures at all the nodes, T1, T2, T3, T4. Okay. Let's assume for this example here that we don't have that much change in between the nodes. Okay. So T1, T2, T3, T4, you know, they probably are not the same, but they're also not that different from each other. Right? And so if you plot it, okay, let me just do between T1 and T2. Okay. And so if these two aren't that different, okay, then when we compute the derivative between these two, right, I'd say it's pretty reliable, right? Because we can just draw kind of a simple line here, and then that's going to be our derivative. Okay? Well, technically, it is possible that, you know, maybe our solution does something crazy. So maybe our solution does something like this, right? And so even though it's possible that, you know, the real solution can have those kind of really wild oscillations, when the endpoints are so close to each other, for most physical problems, which is, you know, what finite elements we're aiming to do, right? And so for most physical equations, you know, the purple line there is very, very unlikely. You know, if T1 and T2 are reasonably, you know, close together, then the chance that you're going to have some oscillations that you're not picking up, and that they end up in kind of the same place is very, very unlikely. And so, you know, if there's not that much change between T1 and T2, you can say with relative confidence that if you draw a straight line, okay, as you're apt to do in finite elements, right, when you assume the solution form, the polynomial form, okay, when you compute the derivative of that line, I would say that's pretty reliable most of the time. Okay. Right. But what's not reliable is if, you know, if they're further apart, which I'll show you on the next page. Okay. Any questions on this? Okay, so let's draw the situation for when they are not so close to each other. Okay. All right, so let me draw a graph, just like I did before, okay? And so let's say that we have T1 here. So let's say that we have T2 up here. Okay. All right, and so in this situation here, we have a pretty high degree of difference between these two, right? And so the most naive thing that you can do is you can just draw a straight line between T1 and T2, okay? And then you can just compute the slope of this line and then call that the derivative, okay? And so that's essentially what finite elements is assuming, right? And so let's say that you have a linear element, and so that's basically what you're assuming. But when you have a high degree of change between them, then there's actually a lot more different things that can happen, right? And so of course you might have this kind of linear change. But another way that they can vary is, let's say that it's much more of a kind of the increase is back-ended. Okay, so let's say that we might have something that looks like this. Okay, or maybe the change is front-loaded, and so maybe we have something that looks like this. Okay, or even though, or you might have something crazy. So maybe it goes like this. Okay? The purple is pretty unlikely, but the blue and the green, I'd say, are both kind of equally likely. And right now, because our finite elements are only solving for the solution values at nodes 1 and node 2, we really have no idea of how the solution is actually varying between these three different options. And it could be any of them, honestly, right? Okay. And so that's kind of crucial information that we're missing. Okay. And of course, if you compare the derivatives, between the red dotted line compared to the blue line and the green line, they're all very different from each other, right? And so if we try to compute derivatives for this, this can be something that's really unreliable. Okay. All right, and so what can you do in these situations, right? And so if you see that you have a very high amount of change or high amount of differences in your finite element solution, what you should do in that case is that should kind of set off a red flag in your head that I need to add more mesh, I need to add more elements here, I need to increase the mesh density. Okay, because let's say that the solution actually followed the blue path here, right? And so if we included more elements, okay, so let's say that we refined the mesh in this area, we made it smaller, okay, right? If we made the elements that much smaller, then we're much more likely to capture that difference because the difference in between solution values is, the distance is much smaller, okay? And in this situations, you're much more likely to compute the derivatives a lot more accurately as well, okay? Okay, any questions on this? Okay. All right, and so let me show you what happens when we've talked a lot about how important derivatives are and things like that. Let me show you kind of one of the symptoms that that you can see from your finite element results that can tell you your derivatives are not being computed accurately. Okay. Okay. Of course, you can check things like the skewness, right? And so that's one metric for mesh quality. But you can also just look at what your solution looks like. Okay. And so I've talked individually with a lot of you about this idea. Okay. But you know, when you're doing finite elements or any kind of simulation, you most of the time you want to avoid situations, or you don't want to see your solution make rapid oscillations between elements. Okay. Okay. And so what I mean by that is, you know, let's say that we have a material like this. Okay. We draw in the element boundaries. Okay. Right. And so if you have a poor quality mesh, you know, you might have a situation that looks like this, where in some elements here, you might get, you know, very high values of stress or deformation or whatever. Okay. But immediately next to them, you're going to have elements that have the complete opposite, right? And so you kind of have this, you know, it almost looks like a checkerboard pattern where it kind of oscillates between high and low, high and low, high, right? And so this is not good, because if you have these kinds of oscillations, this tells me that your mesh needs to be improved in this area, right? And so kind of the best way that you can improve the mesh in this area is usually to make it smaller, okay? Okay. Because remember, you know, what we're modeling in finite elements are physical processes or physical, you know, responses, right? And if you took like a some kind of building and you applied some kind of static load to it, would you expect the stress to go from high and low, high and low, high and low, you know, within that, you know, with that frequency within the structure? You know, most of the time you don't, because, you know, I would say most physical equations and most physical phenomenon, you typically expect, you know, relatively smooth transitions, right? That's not to say that, you know, things can still happen pretty quickly, right? And so you can go from very low value to very high value, but you'll almost never see it kind of jump up and down. That's extremely rare, you know, without any kind of, oscillating forcing or anything like that. You know, it's very rare for it to go high and low like that. Okay. And so if your finite element solutions are kind of showing the same behavior, then, you know, you need to kind of check something. Okay. All right. And so the unfortunate thing with the default settings in ANSYS is that you might not see this all the time. And so ANSYS kind of, you know, does this thing where it kind of, you know, hides these issues, which is, you know, for visually, you know, it makes it look nicer, but it could hide some issues that you might need addressing, right? And so what ANSYS does a lot of times, you know, and it's been doing this, you know, this whole semester, is that it tends to do what's called like a local averaging of the solution. Okay? Okay. Right. And so what that means is that, you know, within a certain vicinity, so let's say that, you know, it's considering the solution for this node that I've marked in green right here, right? Instead of just displaying kind of the raw solution, which is what it got from the simulation, what it does instead is that it kind of takes a weighted average of all the surrounding nodes, right? And so all the nodes that are around it, you know, let's say that it's all of these, it kind of takes a weighted average of all of these together, right? And so, you know, the solution at that particular node, that's going to have the highest weight, of course, but it's also going to factor in all these neighboring ones. And so if you do that for every single node that you have in the entire solution, instead of actually seeing an oscillating solution field like this whole thing just might just, return kind of the middle ground between these, which is just green, okay? And so visually it looks nice because it makes it seem like, everything's hunky-dory and everything's good in the hood and things like that, right? But, we don't just want things to look nice, right? So we want things to actually be correct. And so if you need to check to see if your solution is oscillating like this, you have to turn off this this averaging, right? And so when you go in to view your results, there's a way that you can view your results in an unaveraged way, okay? And so if you turn off the averaging or you make it unaveraged, then ANSYS is not going to do any of this local averaging. And if you do have oscillations in your solution, then that's going to show up as well. Okay. And so it might not look pretty, but it's an important metric for you to check, to see if your solution is good or not. Okay. And in fact, ANSYS knows this, and so ANSYS, it may not show you the unaveraged results by default, but it does take it into account with some of its metrics, okay? And so one thing that you can do to kind of do like a pseudo check on the unaveraged quantity is to check what's called the structural error. Okay. And what the structural error is it's basically a difference between the average solution fields and the unaveraged one. Okay. Okay. Right. And so basically what it's going to do is that, if we use this this figure up here as an example, it's going to just basically take the difference between the the solution that's all green and the solution that has the red and blue oscillations. Okay. If you have a mesh that's high quality, that's producing a good result, then the difference between these two results should be close to zero. Okay. Okay. And so if you have a high quality mesh, then that local averaging that ANSYS does is not actually going to do all that much. And so what you should see is that the structural error there is about zero. Okay. But if you have a poor quality mesh, then the difference between these fields is actually going to be fairly very significant, and you'll see that from the results. Okay. And this idea of a structural error, this is definitely going to make its way into future ANSYS activities for sure. Okay. Okay. Any questions on this? Okay. All right. And so with all that in mind, I think we're ready to kind of state or kind of list out a general kind of meshing approach. Okay. And so to generate a good mesh in ANSYS, a lot of times it's going to take kind of more than one try. Okay. because a lot of the metrics that we use for a good mesh, you kind of have to run a simulation first. Okay. And so, for the kinds of simulations that you'll typically do in ANSYS, where the simulations might take, on the order of like minutes, right? And so you're not waiting like hours for your solution. You have a lot of that gives you, a lot of freedom to really, really make sure you get a good mesh, because you're not waiting for a long time. Okay. And so kind of the approach that I recommend in these cases is an iterative one. Okay. Okay. All right. Because most likely, and especially, when you're first learning, how to mesh, and even for me too, I've been running finite element simulations for, I don't even know how long, close to 10 years now, right? Even it's really hard for me to get a mesh right, or to get a good mesh right from the get-go. And so a lot of times you're going to have to iterate. And so you're going to have to, try something, see how it goes, and then based on the results, refine your mesh and so on and so forth. Okay. Okay. And so here is kind of the 8-step process. Okay. And so first, we generate a initial mesh. Okay. And so it could just be a mesh that uses all the default settings, right? And so I think that's totally fine. And so the default setting is in ANSYS, most of the time will get you a decent mesh. Okay. I take it back. It won't get you a decent mesh, but it will get you a mesh, right? And a mesh is better than no mesh. Okay. Next, you have to apply boundary conditions, right? And so that's, fairly standard. So you have to apply your loads and constraints. Okay. Right. Then you run your simulation. Okay. Right. You let the simulation go, and then you check the results. Okay. And then from the results, you can then identify which areas in your geometry, or which areas in your mesh could use some mesh improvement. Okay. And so some areas where, which can be, improved with the mesh. We've talked about before that if you have a high stress concentration, then that's a good indication that you should refine there. Okay. Okay. Or you can use one of the new metrics that we just talked about, and so you can check for solution oscillations. You can check for high solution gradients, so you can check for structural errors. Okay. Okay. Right. And so you can just, identify those areas. Okay. And so once you have identified those areas, you can then refine the mesh in those areas, or improve it. Okay. Okay. Once you've improved the mesh, and so let's say that you've added some method objects, you've added some sizing objects in those areas, then you can just run the simulation again. Okay. And then after you run the simulation again, you can look at all those problem areas that you had before and just evaluate how well they improved. And then step 8, you just repeat the process until you're happy. Okay. And so you're going to repeat up to step 4. Right, and so you're just going to iterate on this process until until you get solutions and meshes that you're happy with. Okay. All right, and so when you're running ANSYS and you're running the simulations that that only take on the order of seconds or even a couple minutes, then this is a really reliable strategy that you can take to make sure that your mesh is as high quality as possible. Okay. All right, any questions on this? Okay. All right, and so that's mesh quality and all things associated with that. Okay, I do have kind of one word of warning when you're using this process. Okay, and that warning has to do with stress singularities. Okay. And stress singularities is not strictly a finite element thing, but it gets talked about a lot in finite elements. But from just pure elastic theory, what that says is that if you have a very sharp corner, okay, okay. And so when you have, two edges coming together for a structure, and they're coming together at a sharp angle, then, you're going to get a concentration of stresses. Okay. When this corner is exactly a right angle, or so in other words, the radius of curvature is zero. Then the stress that you actually compute there is going to be infinity. Okay. Right. And so that's not just finite elements. That's just elastic theory, just by itself. Okay. And because because finite elements is based a lot on elastic theory, at least for the linear cases, then this means finite elements is going to have the same problem. Okay. And so this goes against a little bit of what we talked about on the previous slide, right? And so on the previous slide, what I said is that, if you have an area of stress concentration, you should just keep refining and refining and refining until you get, a converged solution. But what this is saying is that if you have a stress singularity, what's going to happen is that if you keep refining and refining and refining, your stress is just going to keep going up and up and up and up and up, right? Because, theoretically, the stress there is infinite, okay? Okay. And so, you know, in the last activity, we introduced the idea of a mesh convergence test, right? And so if you have a, a sharp corner, you're never going to reach convergence with the stresses because it's going to keep going up and up and up, okay? In most cases, you're not actually going to get infinity in your finite element simulation unless you really, really refine it there, okay? You're just going to get a really high number, right? And so and the reason for that is, you know, because just by the nature of the meshing process. And so let's say that, you know, we have a sharp corner like this, okay? And just by nature of the meshing process, you know, you're gonna blunt that corner just a little bit, right? And so, you know, you might have an element that might look like this, right? And so instead of coming at a sharp corner, you know, you might have something that kind of blunts it a little bit, okay? But as you refine your mesh more and more, it's going to become a sharper and sharper corner, and that's why your elements go up and up, okay? All right, and so if you are past a geometry, or you do get a geometry which has, you know, sharp corners like this, where you know the stress is going to concentrate, you know, don't try to refine the mesh in those areas. You know, it's just going to be a fool's errand. And so what you should do instead is you should add some fillets or add some chamfers in your geometry, okay? And so, you know, try to avoid running simulations where you have a sharp corner like this, okay? Instead, you know, try to do one with kind of a rounded edge, like that, okay? Okay. Right. That's going to make your life just so much easier if you're just by adding simple fillets to your sharp corners, okay? All right. And believe it or not, you know, this is not strictly a structural mechanics problem too. And so, you know, just because, you know, a lot of my background is in CFD and in computational fluids, you know, even in computational fluids, you want to avoid sharp corners like this too, because what can happen sometimes is that, you know, if the fluid runs towards this corner, it can kind of get just stuck in that corner, right? And that's not good for a lot of reasons, you know, mostly conservation of mass. And so, you know, even for fluids too, you kind of want to round off your corners just to make sure that you don't get kind of weird behavior, because a lot of weird stuff can happen at corners, especially computationally, and you don't want weird stuff most of the time, at least not in your finite elements. You know, yeah, I'll leave it at that. Okay, any questions on this? Any question? Hey, this is a no judgment zone. You know, whatever weird stuff you might be into, you know, just do you do you, okay? But we don't want corners. You don't want weird corners. But you know, whatever other weird stuff you can, that's all you. No judgment here. Okay, all right, so we have about 10 minutes, eight minutes left in the lecture today. And so let's start talking about some of the mesh controls that you have in ANSYS. And so, you know, hopefully this will kind of shed some light on some of the terms, some of the settings that you've been seeing in ANSYS. Okay. Okay. All right, and so, you know, now that we've gone over this idea of quality and you know, what makes a good solution, bad solution mesh. And so I think now is a good time to talk about, you know, what are the options that you have available in ANSYS to kind of make sure that you have as good a quality mesh as possible, okay? And so let's start with just something really basic. And I know a lot of you are already aware of this just because you've been using it in your projects already. But let's kind of formally talk about the difference between global mesh controls and local mesh controls. Okay. All right, so let's start with global, right? And so global mesh controls, these are set from the mesh object, right? And so when you open up your ANSYS project tree, right, the button on the project tree or the project outline that says mesh, a lot of you have already figured out that you can define a lot of settings from here, like the element size and the order and all that stuff, right? And so when you specify settings in the global part, this is going to apply to the entire geometry. Okay. Right, and so this is really useful if you want to set, the element size for the entire mesh for all the parts in your assembly. This is kind of where that you can do it. Okay, and so I would say kind of the two most useful things for this. So there's actually kind of a lot that you can do from this section, but I would say kind of the two most useful settings that you can set globally are a global element edge size. Okay. That's definitely one thing that's really useful. And the other thing that's really useful is the element order. Okay. Okay. Because a lot of times, you kind of know from the start that you're running a structural simulation, and so you need to use a quadratic element, right? And so you can just specify that for the entire mesh, and then you don't have to worry about setting method objects for anything. Okay. All right. And so local mesh controls, change the meshing settings within a particular region. Okay. And so I should say that this is the global mesh controls that applies for everything in your model. But when you can overwrite those global settings for particular regions using the local controls. Okay. Okay. And the way that you apply local controls is to add, additional meshing objects or meshing settings below, right? And so, some of the ones that we've been using kind of the most common ones so far. So these are things like sizing objects, right? Where you specify a certain region in your mesh, where you can specify the size to be something different, okay? Right. Another example of this is method, right? And so if you want to apply a different, a particular element shape or a particular element order in a particular region, so this is another option for a local mesh control, okay? And I think the only other one that we've used is the refinement option, which is kind of another way to kind of refine the mesh in a certain region, okay? All right, and so those are kind of the two levels of mesh controls that you have, right? And so just kind of always remember that the local controls are always going to overwrite the global ones, okay? But the global ones can be used for if for cases where you just want to apply blanket changes, but you're going to apply more refined changes kind of through the local controls, okay? And so usually when I'm first starting out, going back to our meshing algorithm from before, I'll generate an initial mesh using just the global controls. And then as I iterate on the solution more, then I'll add more and more local controls, based on what I see from the solution and where I think I need to add some elements. Okay. All right. Any questions on this? Okay. All right, so in the last 2 minutes, and I just want to kind of mention this first, and we'll pick this up on Wednesday. I do want to answer this quick because I know it's a burning question in a lot of people's mind, is how does the hex-dominant measure work? Right? Because we've talked a lot before that, you know, if you can swing it, and if it's possible within ANSYS, if you can get a hexahedral mesh, then that's you know, that's more preferable because they converge a lot faster and they have a lot more terms in its polynomial, right? And so how does ANSYS actually go about creating a hexadominant mesh? Well, actually, you know, when you specify to ANSYS that you want a hexadominant mesh, ANSYS will actually first create a tetrahedral mesh. Okay. Right. And then what it does, so after it creates the tetrahedral mesh, it will then try to fuse together neighboring tetrahedra to make a hexahedra. Okay. Because if you combine two tetrahedra together, you know, that share a common face, then that actually makes a hexahedra. Okay. And so, of course, you know, this is not going to work all the time. And so that's why it's called hex dominant. And so sometimes, you know, when you specify hex dominant mesh, you'll have some tetrahedra that kind of are on the fringes of your domain. Okay. Or, you know, a lot of times that it just doesn't work. And so, you know, a lot of tetrahedra just aren't able to find partners, or they fuse in a weird way, you know, and then, you know, that's when ANSYS will throw you an error message. Okay. And so when ANSYS gives you an error that it's not able to create a hex dominant mesh, this is the process that's actually screwing up. Okay. All right. Any final questions on this before we wrap it up for today? Okay. All right. So that's all we got time for. So thank you everyone again for being flexible and meeting online. And so Wednesday will also be virtual, unless I send an email. But if I don't say anything, just assume that we're virtual as well. Okay. And so hope everyone enjoys the rest of their evening. And I will see you on Wednesday. Yep. What's up?
Thanks.
Oh, yep. Yeah. Thanks, Jacob. Alex, did you have any other questions? Okay. All right. Yeah. Yeah. No problem. All right. I'll see you on. Oh, all right. I'll see you Wednesday.